All right, hello everyone, and welcome back to Applications of Derivatives. So in this next section, we're going to be looking at the last application of derivatives that we're going to be doing in this class, which is something called optimization. And what optimization is, by its name, you're going to be optimizing quantities. We're going to be figuring out the maximum value that a quantity could take or minimizing a value that a quantity could take. So we're going to be taking real life scenarios and we're going to be maximizing a particular function or we're going to be minimizing a particular function. And which one we want to do depends entirely on the scenario. So to get us started into what optimization is, I think the best introduction is to just actually do a simple optimization problem. So let's say that Old MacDonald has 200 feet of fence, and he wants to use that 200 feet of fence to enclose a rectangular pen for his sheep. We're going to figure out what dimensions of the pen will enclose the maximum area, and while we're at it, we're actually going to figure out what the maximum area of the pen would be. So, just like any other application problem, if you have no idea where to start, I would recommend starting with a picture. So here is a rectangle, pretend that's a rectangle. And since it has different lengths, I'm going to call this length x and I'm going to call this length y. They're different, so I really should use different variables for them. Now, every optimization problem has what is called an objective function. An objective function is what you are asked to maximize or minimize. So in this case, we are trying to find the maximum area. So according to the variables that I used for this problem, the area of this rectangle would be the length times the width, or x times y. So that is the equation that we are supposed to maximize. Now, maximizing involves you finding local maximums. You guys know how to find local maximums. We covered that in another video. Local maximums occur at critical points. You find critical points by finding the first derivative and setting the first derivative equal to 0, and then making sure that it is actually a local maximum by either first derivative test or second derivative test. So that's basically what we're going to eventually do. Now, here's the problem with the way that this equation is written. This equation has two independent variables. Unlike related rates, nothing is actively moving, nothing is actively in motion, and nothing is actively changing. So x and y are not functions of time. Meaning we're not going to have a dx dt or a dy dt or a dy dx. We're not going to use implicit differentiation for this. We have two independent variables. And this is single variable calculus, which means that we can't take the derivative as is. That is where this 200 feet of fence comes in. This 200 feet of fence is what is called a constraint. Now, sometimes the constraints in a problem are built into the scenario itself, and sometimes they are considered separate because it is some sort of limitation that is put on the problem. So the limitation that we have here is that we only have 200 feet of fence. We have a limited amount of fence. So this 200 feet of fence actually applies to the perimeter, which is this x plus y plus x plus y. So I'm going to express this constraint, this limitation, as an actual mathematical equation, which is 2 of those length x's plus 2 of those y's can be equal to 200. Now, in any optimization problem, we're going to use all the materials available, so the perimeter is going to equal 200. That is what is called a constraint equation. And what we're going to do with this constraint equation is we are going to solve it for one of the variables and use it to rewrite the objective function in terms of only one independent variable. And it doesn't really matter which variable you solve for, so I'm just going to solve for x, and I am running out of room here, so if you subtract 2y and then divide both sides by 2, you get x equals 100 minus y. So then what we're going to do is we're going to take this 100 minus y, and we are going to substitute it with parentheses around it in for this x in the objective function. So we'll get the area is equal to x, which I am replacing with 100 minus y, times y. This process is going to involve derivatives, and I really don't want to use product rule, so I am going to distribute that y to give us area equals 100 y minus y squared. This is the same objective function now written in terms of only one single variable with the constraint built in. So with that constraint, our area function is now 100y minus y squared. Keep in mind, y is our independent variable, so we are going to be taking the derivative with respect to y. So, taking the first derivative, we have a prime equals 100 minus 2y. Then what I am going to do is I'm going to start by finding the critical points. The critical points occur where the first derivative is equal to 0. So I'm going to take the first derivative, 100 minus 2y. I'm going to set it equal to 0, and I am going to solve for y. So when you solve for y, you get y equals 50. Now, as I said in previous videos, not every critical point is a local min or max. All we know is that this is a critical point. We're going to hope it's a local maximum because it's the only one we have, but we need to make sure that it actually is a local maximum. And you have two tests for that. You can either use first derivative test or you can use second derivative test. I will say that second derivative test is really easy to use because the second derivative is just the constant -2. So because the second derivative is constant, this function is always concave down. Because it's always concave down, that means x equals 50 feet here is a maximum. By the second derivative test, SDT. Now, since this is a local maximum, this is the value of y that would maximize the area. Now, there are two dimensions here, so we do need to figure out what the other one is. So I'm going to then take our x equals 100 minus y, and I'm going to plug in 50. Gives us x equals 50. So the dimensions that will enclose the maximum area is a 50 by 50 squared. A square is a rectangle, so it does fit the restriction. So your dimensions are 50 feet by 50 feet. Now the maximum area, we're going to take x equals 50 and y equals 50, and we're going to plug both of those into x and y respectively in our area function. So our maximum area is going to be 2,500 square feet. So that is the general gist of optimization problems. You have an objective function, and there will always be some sort of constraint. The constraints might be a separate equation, or the constraints might be built right into the objective function. It really depends on the scenario. So the function that gives the conditions or the limitations is called the constraint function. The function that you were asked to maximize or minimize is called the objective function. Now, to figure out what your objective function is just by reading a problem, you're going to be looking for words like biggest, greatest, maximum, or least, smallest, minimum, shortest, longest. Any of those est words will all signal that this is the objective function. So here are just some general guidelines for optimization problems. Some problems take longer than others. So make sure that you read the problem, and if you don't have a picture, draw one. If you're not given variables, assign variables, and just kind of organize that given information in some sort of picture. Next is to identify the objective function, which is what you're supposed to maximize or minimize. And you're going to write the objective function in terms of the variables in the problem. Now, if the constraint is not built into the objective function, it will be need to written as a separate equation. So you're going to identify the constraints, and if you need to, you're going to write the constraints as a constraint function. And then if you need to, you're going to be solving the constraint function for one of the variables and rewriting the objective function in terms of only one variable. Then, using methods of calculus, meaning find the first derivative, find the critical points by setting it equal to 0, verifying it's a minimum or a maximum using first derivative test or second derivative test. You're going to do all of that to find the absolute maximum or minimum. That's actually really important, that this is an absolute maximum. You might remember from the 4.1 video that an absolute max or min could occur at either critical points or endpoints. I didn't make a big deal of endpoints on that last problem because the endpoints were not plausible for the fence problem. The endpoints for y could be 0, which wouldn't make a rectangle. Or the other endpoint could be 100, which means you put all of the fencing into y, which still wouldn't make a rectangle. So if the endpoints are not plausible, you don't have to check them. But if the endpoints are plausible, you absolutely need to check them. A couple of other notes before we do more examples. Before you take any derivatives, make sure that your objective function is only in terms of one variable. If it's not, you got to use the constraint function to rewrite it all in terms of one variable. Then you're going to set the derivative equal to 0 and solve for that variable. You do need to make sure that it is actually a maximum or minimum using either the first derivative test or the second derivative test. Now, don't forget, if your endpoints are plausible, you need to test them. Please always figure out the endpoints, the extreme low value for your variable and the extreme high value for variable. Some critical points might be outside the domain and need to be eliminated because they wouldn't make any sense. Some critical points will end up being endpoints, which may not make any sense. But if your endpoints are plausible, you must check them and find the absolute extrema. So, you have to check the endpoints if they are plausible. So, for this next one, very similar idea. We have 400 feet of fence this time, and we're going to construct a rectangular corral. That looks something like this picture. One side of the corral is going to be formed by a barn, and the barn does not need a fence. So the fencing here is the 4 lengths of X that you see pictured and this length of Y. So there are going to be 3 exterior fences and 2 interior fences are going to partition the corral into 3 rectangular regions. We're going to figure out what dimensions of the corral will maximize the enclosed area. So right away, we are asked to find the maximum area. We're going to neglect the thickness of the interior fencing, so the area is just going to be the length y times the width x. So the objective function is going to be the area equals one dimension x times the other dimension y. Let's try that again. The area is equal to x times y. Now, x and y are not functions of time, they are each independent variables. So we cannot take any derivatives right now because we can only differentiate with respect to one variable. So that's where the constraints are going to come in. The constraint is this 400 feet of fence. Now remember, the fences are formed by those 4 x's that you see there, plus that 1 y, can be equal up to 400, and we're going to use all the materials available. So then I'm going to solve this equation for one of the variables. Y is the easiest variable to solve for, so subtract 4x from both sides. We get y equals 400 minus 4x. So I'm going to take 400 minus 4x, and I'm going to substitute it in for y in my objective function with parentheses around it. So area equals x times 400 minus 4x. I don't want to use product rule, so I'm going to distribute x. So I have area equals 400x minus 4x squared. Then I'm going to use methods of calculus to find the maximum. So I'm going to take the first derivative. So the area, A prime, is equal to 400 minus 8x. I'm going to find the critical points by taking the first derivative, 400 minus 8x, setting it equal to 0, and solving for x. So if you solve this for x, you get x equals 50. Let's try that again. If you solve this for x, you get x equals 50. I'm sorry, I have a glitchy stylus and I don't know how to fix it. However, remember, not every critical point is a local maximum. You have to make sure that this actually is a local maximum. So what we're going to do is we're going to either use first derivative test or second derivative test to make sure that this is a local maximum. Second derivative test is really easy to do, so I'm just going to do a quick second derivative test. So the second derivative is negative 8. Because the second derivative is always a negative number, this function is always concave down. Concave down means that is a local maximum. So x equals 50 is a local maximum. By the first derivative test. So then let's make sure that we fully answer the question, what dimensions, plural, so we need to actually go find the other dimension. So x equals 50 will be the x dimension that encloses the maximum area. To find the y dimension, we're going to take 50 and we're going to plug it back into this y equals 400 minus 4x. So y is going to equal 400 minus 4 times 50. Gives us a y value of 200. So the dimensions that maximize the area are that x equals 50 feet and that y equals 200 feet. Then for the maximum area, we're going to take 50 and plug it in for x in our area function, and we're going to take 200 and we're going to plug it in for y in our area function. So the maximum area is going to be 10,000 square feet. Now let's move it into 3 dimensions for this next one. Let's say that an airline policy states that all baggage must be box-shaped with a sum of length, width, and height not exceeding 64 inches. We're going to figure out what dimensions and volume of a square-based box will give us the maximum volume under these conditions. So it's a box, so let's draw a picture. Drawing a box with a glitchy stylus. This is going to be fun. Oh, that wasn't that bad. All right, so it is a square base, which means the base is a square, which means this length here and this length here are going to be the same. So I'm just going to call them the same variable, x and x. Now, it didn't say anything about the height being the same. It may not be, it might be, we don't know. So I'm going to call the height a different variable, let's say h. Now let's figure out what our objective function is. Greatest volume. So we are supposed to maximize the volume. Now according to the variables that I have assigned here, the volume is going to be x times x, which is x squared, times the height h. And this is going to be our objective. So that's our objective function. Now here's the issue. The objective function is, once again, in terms of multiple variables. So we're going to have to use a constraint function to rewrite the volume equation in terms of only one variable. That's where the 64 inches comes in. The sum of length, width, and height can be up to 64 inches. And we're going to use all of the materials available, and we're going to use the 64 inches. Because I don't know about you, but when I go to an airport, I try to bring the biggest bag possible that will fit in the, the little metal grate there. So I will bring the biggest bag possible. Let's use all of the 64 inches. So here's our constraint function. The sum of length, width, which is 2x plus x, which is 2x, plus the height can be up to 64 inches. So then I'm going to solve this constraint function for one of the variables. H is really easy to solve for, so just subtract 2x from both sides and we get h equals 64 minus 2x. So then I'm going to take this 64 minus 2x and I'm going to plug it back in for h in our volume function. So volume is going to be x squared times parentheses 64 minus 2x. And I don't want to use product rule, so I'm going to distribute the x squared, so I get the volume equals 64x squared minus 2x cubed. Then I'm going to take the derivative. So the first derivative, v prime, is going to be 128x minus 6x squared. Then I am going to take this and set it equal to 0 and solve for x. So you might notice that there is a common factor of 2x here, so I'm going to take a 2x out of each of these terms, leaving me with 64 minus 3x equals 0. That'll actually give me two critical points. One of them is x equals 0, and the other one is going to be 64 over 3. Now here's the thing. We're going to start eventually making a big deal about the endpoints. The variable that we just differentiated with respect to was x. So this x equals 0 here, would it really make any sense to have the x length be 0? No, it wouldn't. This is actually one of your endpoints. So one of your endpoints here was 0, meaning you put none of the 64 inches into x and that would not make a box. Now the extreme value on the other end, the extreme high value, would give us another endpoint of 32, which would mean that you put all of the 64 inches between those two x's, meaning you wouldn't have a height and you wouldn't have a box. So the endpoints are not plausible, so we don't need to check them. And because one of your critical points ended up being one of those unplausible endpoints, we get to throw it out. Which means the only candidate for our maximum is this 64 over 3. So we have to make sure that this is a maximum. Now I am aware that this video is starting to get a little long, so you do just need to make sure that this is a local max. It is. You can use either first derivative test or second derivative test. It is up to you. So let's make sure that we finish answering the question, what are the dimensions and volume of the greatest, the box with the biggest area? So the dimensions, there's one of them. To get the other one, we're going to plug 64 over 3 into this h equals 64 minus 2x. So the height is going to be 64 minus 2 times 64 over 3. And we actually get a height of 64 over 3. It ends up being a cube. A cube will enclose the maximum area. So your dimensions are going to be 64 over 3 inches by 64 over 3 inches. And the volume, plug 64 over 3 in for both x and h, and we get a volume of, this is very approximately, it is approximately 9,709 cubic inches. Now for this next one, this is going to be an example where the constraints are actually going to be built right into the objective function, because when you deal with something that is a limited size and you're only working with this one thing that is a limited size, you're going to find that a lot of times the constraint function is built right into the objective function. So we have a square piece of cardboard that is 10 inches on one side is used to make an open top box. So here's basically what's going on here. We have a square, which means that each side is 10 inches long. So this side is 10 inches and this side is also 10 inches. What's going on is that we're going to take squares of equal size, and we're going to cut squares of equal size out of each of these four corners. Once those are cut out, we're going to then take this, each of these lengths here, they are going to be folded up, and it will make a box with no lid. That's basically what we're doing here. So once these squares are cut out, and I'm going to call each of these squares, I'm going to call their length and their width x. And since they're squares, it's the same on both sides. We're going to find the length of the square that's cut out of each corner. That will give the maximum volume. So we are supposed to maximize the volume equation. Now, according to the variables that I have here, once these squares of length x are cut out of each corner, the remaining side, which will be from here to here, is going to be of length 10 minus 2x. And then same thing over here. Once these squares of length x are cut out of each side, this length here is going to be 10 minus 2x. So when this is folded up for the volume, the length is going to be 10 minus 2x. The width is going to be 10 minus 2x. And when these flaps are folded up, the height is actually going to be x. So length times width times height, x. And if you take a look at this volume equation, we are going to be taking its derivative. There's only one independent variable here, x. The constraint was the fact that the cardboard was a fixed size. So because the cardboard was 10 inches on each side, that constraint was built right into the objective function. So we do not need a separate constraint function here. We can just take the derivative as is. Now, I really don't want to use triple product rule, so I'm going to do a whole lot of distributing. So I'm going to FOIL this 10 minus 2x times 10 minus 2x, and then I'm going to distribute the x to each term. So that will actually give us a volume equation of, FOIL first, we've got this 100, and then minus 20x minus another 20x is a minus 40x, and then negative 2x times negative 2x is going to be plus 4x squared. Then I'm going to distribute x to each term, so I get volume equals 100x minus 40x squared plus 4x cubed. So then I'm going to take the first derivative, and I'm going to end up finding the critical point. So for the first derivative, we have 100 minus 8x plus 12x squared. Then I'm going to find the critical points by taking the first derivative and setting it equal to 0. So I'm going to also put this in standard form. So I've got 12x squared minus 8x plus 100. I'm going to set it equal to 0, and I am going to solve for x. So let's take out a common factor of 4. So we have 3x squared minus 2x plus 25. Then let's factor it. So when we factor it, we're going to get 3x minus 5 times x minus 5. That will give us two critical points. One of them is x equals 5/3, and the other one is x equals 5. Remember, 4 never equals 0, so that greatest common factor that we took out, we can ignore it. Now here's the thing. Always keep in mind the endpoints. The endpoints are the extremely small and extremely large values for our variable x. Now, x is the size of the square, of the length of the square that's cut out. So one of the endpoints of our closed interval is 0, meaning we don't cut a square out, which means we can't fold it to make a box, so that's not plausible. The other extreme end is that x equals 5, which means we cut out 5 inches on the left, 5 inches on the right, which would cut the whole side off and would not form a box. So the endpoints are not plausible. Because the endpoints are not plausible, we don't need to check them. Now x equals 5, hey, there's one of those not plausible endpoints, so we get to throw that out. That won't make a box. So that means our only candidate to give us a maximum is 5/3. So we are going to make sure that this is a local max. You can use either first derivative test or second derivative test. It is up to you, but you do need to use one of them. Now that you have determined that this is a local maximum, the length of the square that is cut out of each side should be 5/3 inches, and that will give you the maximum volume. It didn't actually ask what the maximum volume is, so that's all it was asking for. Now, for a problem like this, if it involves formulas that you don't use on a regular basis, I will give you any formulas that you would need. Things like volume of a box or area of a rectangle, I really do expect you to know that. But if you need, arc length, which is what this problem needs, I would give you that formula. Or chord length, which is also something this problem needs, I would give you that formula. So I will tell you right away that we are going to need arc length, which, if you remember from pre-calc, arc length is going to be equal to r times the central angle theta. And then we also have chord length, which the chord length is going to be 2 times r times the sine of theta over 2. All right, so now that I got those out of the way, let's actually go through this and figure out what this question is asking and what we are supposed to maximize or minimize. So let's say that you are standing on the shore of a circular pond, and because this is calculus 1, this pond is a perfect circle. And the pond has a radius of 1 mile, and you are trying to get to a point on the shore directly opposite your position on the other end of the diameter. So you are here, and you want to get here. You plan on swimming, and you know that you can swim at about 2 miles an hour from your current position to another point P on the opposite shore. Now, we don't know where it is. It could be here, it could be, further up. We don't know where it is, but there's some other point P on the opposite shore. So this length right here is the swimming length. Then you plan to get out of the water, and you know that you can walk at about 3 miles an hour. And you plan on walking about 3 miles an hour along the shore the rest of the way until you get to the finishing point. So the walking distance is that curved arc right there. How should you choose P to minimize the total time? So instead of finding a maximum, we're going to be finding a local minimum. And we're going to be minimizing the total time for the trip. Now, I see distances, I see speeds, I see time. So there is a very simple relationship between velocity or speed, distance, and time that we could use. Velocity, or speed, is equal to the distance traveled divided by the total time traveled. So if you solve this for t, you get the total time traveled is equal to the distance traveled divided by the speed. So that's what we're going to use. Total time, let's try that again. Oh my God. Total time is equal to the distance traveled d divided by the speed or velocity v. Now, since we can walk and swim at two different speeds, we're going to have two different time equations, one for walking and one for swimming. And then to get the total time, we're just going to simply add them together. So let's start with the swimming time. The total time that it takes to swim is going to be the swimming distance divided by the swimming speed. Now the swimming distance, that is this length right here. This is what is called a chord. A chord is just a line segment that connects two points on the outside of a circle. Technically, a diameter is a special type of chord. Now, this point P is determined by this central angle theta. Because if we put P, let's say over here, theta is going to be bigger. If we put P over here, theta is going to be smaller. So that point P is going to be determined by how big we want that central angle theta to be. The bigger the theta, the further we swim. The smaller the theta, the shorter the swim distance. So we're going to use the chord length formula, which I provided you, with a radius of 1, and theta is going to be our independent variable. So the total swimming distance is going to be 2 times the radius, 1, times the sine of theta over 2. So that's the swimming distance, divided by the swimming speed. The swimming speed is that 2 miles an hour. And because we are going to be taking derivatives, I am going to make sure that I do as much simplifying as I can. So, that cancels with that, giving you the total swimming time is just equal to the sine of theta over 2. Then we're going to do that again for walking. So the total time spent walking is going to be the walking distance divided by the walking speed. So the walking distance is going to be this length right here, which is called an arc. An arc is a piece of the outside of a circle. So the arc length formula is right here. Now, regardless of whatever you chose theta to be, the central angle that will form the walking arc is going to be pi, because remember this is in radians, minus theta. So pi minus theta, whatever your theta ends up being, that is going to be the central angle that will form the arc that you are going to walk along. So the total walking length is going to, the total walking distance is going to be the radius of the pond, which is 1, times the central angle that formed the arc, pi minus theta. Then we're going to divide that by the walking speed, which is 3. And I do need to keep in mind I'm going to be taking derivatives, so let's do a little bit of rewriting here. I'm going to split up that subtraction in the numerator as pi over 3 minus 1/3 theta. Just doing a little bit of rewriting so that our derivative is not going to be that terrible. Now, let's put the two of them together into a total walking equation, and it looks like the only variable that we really have here is theta. So we don't need a separate constraint function because the total time equation is only in terms of one variable. The constraints here were the fixed swimming and walking speeds and the fact that the pond was a fixed size. So because we had all of these fixed quantities built right into our objective function, we do not need a separate constraint function here. So I'm just going to take the swimming time, which is that sine of, I'm going to rewrite theta over 2 as 1/2 theta, plus the walking time, which is pi over 3 minus 1/3 theta. Then I'm going to find the critical points by taking the first derivative and setting it equal to 0. So the first derivative, t prime of theta. Sine of theta over 2 is going to require the chain rule. The outside function is sine and the inside function is 1/2 theta. So the derivative of the outside function is cosine of the inside left alone You can write it as 1/2 theta if you want. It doesn't matter. Then we're going to multiply it by the derivative of the inside. The derivative of 1/2 theta is 1/2. Then plus derivative of pi over 3. Remember, pi over 3 is a constant. Its derivative is 0. So then minus derivative of 1/3 theta is 1/3. So then we are going to take this derivative, we are going to set it equal to 0, and we are going to solve for theta. And this is actually a trig equation. You might remember, to solve a trig equation, we need to get the trig function by itself first. So I'm going to add 1/3 to both sides, so I have 1/2 cosine of theta over 2 equals 1/3. Multiply both sides by 2 gives us the cosine of theta over 2 equals 2/3. Then, to get rid of cosine and get theta over 2 by itself, we are going to take the cosine inverse of both sides. So that gives us theta over 2 equals the cosine inverse of 2/3, which we will figure out later on a calculator. Remember, the mode you need to be in is radians. Then we're going to finish getting theta by itself by multiplying both sides by 2. So then on a calculator, you can do cosine inverse of 2/3, then multiply it by 2, and you get theta's, very, very approximately equal to 1.68 radians. Now, before we move on to making sure that this is a maximum, you always have to keep in mind the endpoints. For the endpoints, theta is our variable here, and theta is the central angle that formed the point P where we got out of the water. Now, one extreme value of theta is 0. If theta equals 0, that means you don't do any swimming. That means you walk the whole way, which is completely plausible. You could walk the whole way and just not swim. The other extreme value of theta is 180 degrees, or pi in radians, which would mean you don't walk, you just swim directly across the diameter, which you might not want to do, but you could do it. It is plausible. So your endpoints are plausible. Because your endpoints are plausible, you must check them. Keep in mind, we're finding the absolute minimum. We are minimizing the total time. So we're supposed to find the absolute minimum of the total time equation. So if you remember from section 4.1 how to find an absolute minimum, what we're going to do is we're going to make a table of values. We're going to take our theta and our t of theta, and we're going to plug in both of our endpoints and our one single critical point, so 0, 1.68, and pi. We're going to plug each of these into the original total time equation, this right here, this t of theta. Whichever one of these has the smallest t of theta is the smallest amount of time and will minimize the total time equation. So if you plug 0 into t of theta, you get sine of 1/2 times 0 plus pi over 3 minus 1/3 times 0, which gives you pi over 3, which is approximately, about 1.05. Then if you plug in 1.68 into each spot that you see a theta, you get a total time of approximately 1.23. And then if you plug pi in, so sine of pi over 2, which is 1, plus pi over 3 minus pi over 3 gives you 1. So which of these has the smallest y-coordinate, the smallest t of theta? It's actually that one. So the absolute minimum here is this pi comma 1. So how should you choose p? That central angle should just be pi. So you really should swim the whole way. If you swim the whole way, as much as you probably don't want to do it, it will minimize the total time. So swimming the entire length will minimize the total time equation, and you just shouldn't walk at all. So the absolute minimum in this problem actually ended up being one of the endpoints, which is why anytime the endpoints are even remotely plausible, you must always check them, because they could actually be the absolute maximum or minimum respectively. Now for this last one, let's say that you are a civil engineer and you are on a planning committee to build a road that joins a ranch to a particular highway, and the highway will connect to the city over here. That will enable drivers to reach the city in the shortest time. So our objective is we are minimizing time again. Remember, the total time traveled is equal to the total distance traveled divided by the traveling velocity or speed. And we're supposed to figure out how should this be done if the speed limit is 60 kilometers an hour on the road and 110 kilometers per hour along the highway. And it is known, probably from surveying, that the perpendicular distance between the ranch and the highway is 30 kilometers. And we do know that from this point P, from that perpendicular, the city is 50 kilometers down the highway. So the road is actually going to be some diagonal length here that connects the ranch to this point Q. Now Q is where they're going to put the entrance ramp on the highway from that back road. So Q could be here, it could be, way over here. Q is just going to be somewhere along this highway. And a little Pythagorean theorem, the length x is that distance between the perpendicular and wherever we put the entrance ramp. So x is going to be our variable. And a little Pythagorean theorem gives us the length of the road to be the square root of 30 squared plus x squared. So because these are two different, hold on, I don't know what's going on with the subtitles. Give me one moment. I have to pause it. Okay, let's try that again. Hopefully the subtitles will play along this time. So hold on. Yeah, so let's hope the subtitles will actually cooperate this time. So because we have two different types of roads with two different speed limits, we're going to have two separate time equations, and then we're going to add them together for a total time equation. Our variable here is going to be this length x. X is going to be determined by where we put the entrance ramp at Q. So Q could be here, 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 wherever. Wherever we put Q, that will be our length x. So let's start with the total time along the back road. So the total time spent driving along the back road is going to be the distance along the back road, which is that square root of 900 plus x squared, divided by the speed limit along the road, which was that 60 kilometers an hour. Then, for the total time spent on the highway, the total time spent driving along the highway is going to be the highway distance divided by the highway speed. Now, wherever this Q is put, the rest of the time spent driving along the highway is going to be this 50 minus x. So the total highway distance that these people will travel will be 50 minus x divided by the speed along the highway, which is 110. And I am going to break this up a little bit because we are going to have to take derivatives into 50 over 110 minus 1 over 110x. So then I'm going to take these two separate time equations and I'm going to add them together into a total time equation. So the total time And I'm going to do a little bit of rewriting, just keeping in mind derivatives. So I'm going to rewrite the total time equation as the time spent driving along the road, which is 1 over 60 times 900 plus x squared to the power of 1/2 plus the time spent driving along the highway, which is that 50 over 110 minus 1 over 110x. Now I get to take derivatives. So now I'm going to take the first derivative. So that constant multiple of 1 over 60 can just stay there. This is going to require the chain rule. So the outside function is the power of 1/2. The inside function is 900 plus x squared. So the derivative of the outside function is going to be 1/2 times the inside left alone. And then we're going to decrease the power by 1, gives us negative 1/2. Then we're going to multiply it by the derivative of the inside. Derivative of 900 plus x squared is 2x. Then derivative of 50 over 110 is 0. Minus derivative of 1 over 110x is 1 over 110. Then I'm going to set this equal to 0, and I'm going to start solving for x. Now, just doing a little bit of simplifying, we can cancel the 1/2 and the 2 out. And I am actually going to rewrite this 900 plus x squared to the power of negative 1/2 as a square root in a denominator. So just doing a little bit of rewriting. I'm going to come over here. I'm going to have x over 60 times the square root of 900 plus x squared. Then minus 1 over 110 equals 0. And I will give you the suggestion of adding 1 over 110 to both sides. So it'll look something like this. We have x over 60 times the square root of 900 plus x squared equals 1 over 110. It may not look like this did much, but what we can actually do is this is a proportion, and we can solve a proportion by cross-multiplying. So I'm going to cross-multiply this and get an equation that I can then finish solving. So cross-multiply, this way we get 110x equals 1 times all this mess is just 60 times the square root of 900 plus x squared. Now I am out of room, so I am going to go on to another slide. So just give me one moment. We need a little more room than this. All right, so what we can then do is we can, because 110 and 60 are both divisible by 10, we're just going to basically divide both sides by 110. So give me 1 second. So if we take this 110x equals 60 times the square root of 900 plus x squared, let's divide both sides by 10, cancel out a couple of zeros here. So we have 11x equals 6 times the square root of 900 plus x squared. Then one of the variables that you're trying to get by itself is inside of a square root. How do you get rid of a square root? You're going to square both sides. So I'm going to take both sides and I'm going to square both sides. Remember, when you take a product and raise it to a power, you can simply take each part of that product and raise it to that outside power. So 11 squared is 121 times x squared equals, there's multiplication right there, so we can do that over here too. 6 squared is 36 times square root and square will cancel each other out, leaving you with parentheses 900 plus x squared. Then we're going to start getting x squared by itself. So what I'm going to do is I'm first going to clear out those parentheses by distributing the 36 to each term. So we're going to have 36 times 900, which is, just give me a second, so 36 times 900 is 32,400. Then 36 times x squared is plus 36x squared. Then we're going to move all of the x's onto one side, so I'm going to subtract 36x squared from both sides. So 121x squared minus 36x squared is going to be 85x squared equals 32,400. Divide both sides by 85 and take the square root of both sides. We get x is approximately equal to 19.52. Remember, this is a critical point. We have no idea if this is the absolute minimum or not. Now, going back to the picture, we do have to keep in mind endpoints for every single one of these problems, because every single optimization problem involves you finding an absolute extrema. Absolute extrema can occur at either critical points or at endpoints. Remember, x is that distance between the perpendicular at P and the entrance ramp at Q. So one extreme value for x is x equals 0. If x equals 0, that means the road goes straight down the perpendicular, and then the entrance ramp is here at P, which is totally plausible. You can have that. You can do that. So yeah, 0 is possible. The other extreme value for x is we make x equal to 50, which means the road would go something like that. Probably not the fastest, but could you do it? Is it physically possible? Yeah, it is physically possible. So x equals 50 is the other extreme for x. And because these endpoints are plausible, you must check them. Remember, we are trying to find an absolute minimum because we're trying to find the shortest time, so we're finding the absolute minimum. So to find the absolute minimum, what we're going to do is we're going to make an x and t of x table. We are going, that's t of x. We're going to take our critical point and each of our endpoints, so 0, 19.52, and 50. You are going to plug each of them into the total time equation, this t of x. Whichever x value gives you the smallest t of x value will minimize the total time. So we're going to plug each of these into the total time equation. So if you plug in 0, you get 0.95 hours. If you plug in 19.52, you get approximately 0.87 hours. And if you plug in 50, you get 0.97 hours. So there's not a whole lot of difference between these, but that is the absolute minimum. So how should this be done? X equals 19.52 kilometers will be the shortest amount of time. So if you put the entrance ramp at 19.52 kilometers away from the perpendicular, that will minimize the total time equation and will allow drivers to reach the city in the shortest amount of time. So that is it for optimization. Thank you all so much for watching. And if you have any questions, please feel free to email me, and I will see you in the next video.